There's any number of languages in which we can communicate, English being just one of them. But computers, of course, only understand binary, zeros and ones. And so somehow we have to communicate our thoughts ultimately in binary in order to solve some problem with a computer. But certainly we don't want to program computers by writing zeros and ones and memorizing the patterns that they'll understand. So we do somehow need to adopt a process via which we can express our thoughts and the solutions to the problems that we have in mind, but in such a way that the computer can understand them. Now, it turns out it's quite meaningful when you see something like Intel Inside or AMD or any number of other computer manufacturers that make what are called CPUs, central processing units, which you can think of as the brains of sorts inside of your computer. Well, it turns out that Intel and AMD and other companies have decided in advance what patterns of bits, zeros and ones, that their CPUs understand. A certain pattern of zeros and ones might represent addition. Another pattern of zeros and ones might represent subtraction or multiplication or division, or the act of moving information around in memory or saving information from memory. And so those patterns are very much computer or CPU specific. And frankly, I'd like to be able to write software and write code that can run on your computer and my computer and some other manufacturer's computer without really having to know all about those zeros and ones. So there too, it would be nice if there's a process, a workflow, a tool chain via which we can communicate our thoughts in a fairly accessible way, but have them ultimately translated into those zeros and ones. So what is it that Intel Inside really means? What is it that a CPU actually understands? Well, it's what's called machine code, zeros and ones that ultimately dictate what the computer should do, add, subtract, multiply, or something else altogether. That machine code literally might look something like this. In fact, let me give you just a moment, and from all of these zeros and ones, can you glean, perhaps, what this very program would do if run on a computer? No? Well, odds are you couldn't imagine what this would do, because even I can't read these zeros and ones. But if it turns out you fed these very zeros and ones to a computer, it would print out on the screen, quite simply, "Hello world," which is sort of the canonical phrase, one of the first phrases ever printed on a computer screen back in the day when computer languages were first being invented. Now, you, of course, would never know that, should never know that, nor should even the most sophisticated of programmers, because this is just too low of a level to communicate one's thoughts in. Far more compelling would be to operate at a level closer to English or whatever your spoken language might be. And so quickly, when humans invented computers decades ago, did we decide we need something different from machine code. We need something at a higher level of abstraction, if you will, something that's more familiar to us, but that's close enough that the computer can somehow figure out what to do. And so thus was born assembly code. Assembly code is an example more generally of what's called source code, which is typically English-like syntax, more familiar to us humans, that can somehow be translated eventually down to machine code. And assembly code, which was one of the earliest incarnations of this general idea, looked a little something like this. Now, it too looks pretty cryptic, though hopefully not quite as cryptic as just seemingly random patterns of zeros and ones, because there is some organization to this text here. It's not quite English-like, I would say, but there's some familiar sequences of characters that I can perhaps ascribe some meaning to. I see words that look a little familiar: push Q, or at least push, move Q, or perhaps move, sub, maybe that means subtract, or call, as in to call a function or a procedure, XOR and add and pop and others. These seem to be reminiscent of English words, and so while cryptic, and I would surely need a manual in order to figure out what these mean, this is a standardization of how you might communicate instructions to a computer. Indeed, all of those key words, push Q, move Q, sub Q, and so forth, are literally called instructions. And those are the names given to the instructions, the commands that Intel and AMD have decided that their brains, their CPUs, shall understand. To the right of these instructions is some cryptic-looking syntax now, dollar signs and percent signs, commas, and others. Well, those are used to communicate what are called registers. It turns out that the smallest unit of useful memory typically inside of a computer in particular inside of a CPU, is what's called a register. A register might be 8 bits back in the day, 32 bits more modernly, or even 64 bits. And that is really the smallest piece of information that you can do some operation on. The smallest unit of information that you can add to something else or subtract from something else and so forth. So when a CPU is doing its arithmetic, addition, subtraction, multiplication, division, and so forth, it's operating on pretty small values. They might be big numbers, but they only take up maybe 32 or 64 bits. And those registers, those chunks of memory, have names. The names, to be fair, are cryptic, but they're expressed in this same language, assembly code, so that you're telling the computer in this language, what should you move to where, and what should you add to what. And so once you acquire a taste, if you will, for this language, does all of this begin to make more sense? And frankly, if I really scour it, aha! Down here at the bottom, I do see explicit mention of that phrase, hello world, and these other lines simply call into action the printing of that phrase on the screen. But frankly, this doesn't look all that compelling still. It's certainly better than zeros and ones, but assembly code is generally considered to be fairly low level. Not as low level as zeros and ones, and not as low level as electricity from the wall, but it's still low level enough that it's not really that pleasant to program in. Now, back in the day, decades ago, this was all you had at your disposal, and so surely this was better than nothing else. And in fact, some of the earliest games and some of the earliest software were written in assembly language. So it truly was experts back in the day writing frequently in this low language, and you might still use it today for the smallest of details. But on top of assembly language have evolved more modern forms of source code, newer languages with easier to understand syntax and more features. And one of the first successors to something like assembly code was a language called C. Quite simply, C looks like this. Now, I dare say this too remains fairly cryptic, but I feel like we're walking up a set of stairs here where things are finally starting to look a little more familiar and a little more comfortable, even though there might still be some distractions of syntax. These angled braces and these curly braces and quotes and parentheses and a semicolon, all of that you might get to in an actual course on programming itself. But here, we use this as demonstrative of a fairly more English-like syntax with which you can express the same program. Printing hello world in a language called C can be implemented with precisely this code. But frankly, we're starting to stray pretty far from that low-level language that computers ultimately understand and need to accept as their input, binary. So how do we get from this higher level language, so to speak, called C, down to those zeros and ones? Well, frankly, the process by which this happens tends to make an intermediate stop in what's called that assembly language. So a human might write code like this, like I did here in C. You might then use a program that converts this C code to assembly code, and then another program that converts that assembly code down to those zeros and ones. And frankly, you could probably use a tool that does both of those steps at once so that it creates the illusion of going directly from this to so-called machine code, those zeros and ones. So let's take a moment and actually do that on my computer here. This is a process that you can do on a Mac or a PC, running Mac OS, Windows, Linux, or any number of operating systems. I happen to be doing it on a Mac here, and I'm going to use a fairly common program these days called a text editor. This is a very lightweight version of a word processor. It doesn't have bold-facing and underline and italics. It really just allows you to type text, but it does tend to colorize it for you to draw your attention to the disparate parts of a program. And I'm also going to open up what's called a terminal window. A terminal window is a keyboard-only interface to what your computer can do. So while I still have access to my mouse, it's not going to be all that useful for this environment, because anytime I want to run a program or execute a command or make my Mac do something, I'm going to have to do it from my keyboard alone. Let's take a look. Now here I am in front of my text editor, and I'm going to go ahead and create a file called, say, hello.c. .c being a conventional file name to indicate to the computer that the code I am about to write is going to be implemented in that language called C. Now at the top of this program is where I'm going to write my code, and I'm simply going to transcribe what we just saw. Include standard io.h, int main void, open curly brace, followed by a closing curly brace ultimately, and then printf, quote unquote, hello, comma, world, \n, Finally, a semicolon. So here I've written my source code, and indeed it's been colorized by the text editor simply to draw my attention to disparate parts of this program. And were we to dive deeper into C in particular, we'd see what each of these different symbols mean. But for now, let me propose that we only care about what this program is meant to do, which is to print ultimately, hello world. But all I've done is write a program in C. I somehow have to get it to its form of zeros and ones that the computer ultimately understands. So it's not sufficient just to save the file, because indeed all that's been saved are these letters and symbols in some file called hello.c. I somehow have to convert that file to zeros and ones. Well, it turns out that there exist tools called compilers. A compiler is simply a piece of software written presumably by someone else that knows how to understand C, perhaps knows about assembly code, but definitely knows about those patterns and ones that Intel and AMD ultimately require that I output in order to get them to execute commands. So how do I go about compiling hello.c? Well, it turns out installed on my computer, and perhaps even yours, is a program called CC. The C compiler, if you will. Compile simply referring to this process of translating one language to another. And so I'm going to go down here to the lower portion of my screen, wherein I have a prompt, a $sign that, for whatever historical reason, simply represents a prompt in a terminal window. And it's in here that I can type these textual commands. cc-o hello space hello.c. A fairly cryptic incantation of commands, but ultimately, this has created a new file on my computer called, quite simply, hello, with no file extension. Now, on a typical Mac or PC, when you want to run a program, you would typically just double-click its icon, and it would be loaded up, and you would see its ultimate behavior. But here in this command line interface, so to speak, wherein I can only type commands textually, I have to tell the computer to run this program only via my keyboard. And the convention via which you can do this is quite simply to say /hello, where dot refers to the current folder or directory in which this file is. The slash just separates that from its name. And hello, of course, is the name of the program I've written. And here we go. With a stroke of enter, I now see hello world. And thus was born my very first program in C. Of course, it took me quite a while to get to this point, and I didn't necessarily even understand all of those lines of code along the way, but I did understand that my goal at hand and the problem to be solved was to print quite simply hello. But there's a bit of overhead, of course, to a language like C, wherein there's not only the syntactic complexity of it, but that, frankly, gets much more familiar over time. There's also this additional step, this middleman, a compiler that has to exist and somehow translate your source code to machine code. In fact, what we've effectively done just now is this. If up here is my so-called source code stored in any file, for instance, hello.c, and I want to convert it ultimately to so-called machine code, the zeros and ones that my computer understands, I somehow have to get from top input to output. And the middleman here is, again, this tool called compiler. In the context of my having written this program in C, I used a program, a compiler called CC, but any number of other options exist. You might have heard of Visual Studio, perhaps, or Eclipse, or yet others still. This middleman simply takes as input that source code in C and produces as its output that machine code that the computer expects. And so when I type that command, cc-o hello.c, it ultimately was telling my computer, take as input hello.c, produce as output a new file called hello, inside of which are those zeros and ones. Now, not all languages operate like this. It turns out that more modern languages skip that step of compilation altogether, or at least hide that detail from the user so that he or she doesn't necessarily need to know how to compile their code. It's handled more automatically. Now, some languages instead use not a compiler, but an interpreter. Whereas a compiler takes as input one language, like C, and produces as output another language, like machine code, an interpreter instead takes as input some source code and then runs it, or interprets it, line by line, top to bottom, left to right. And whenever it sees an instruction like print, it thinks to itself, oh, I know how to print something on the screen, and it goes and does it on behalf of that source code. It does not, strictly speaking, convert those instructions instead to zeros and one. It is instead the interpreter itself, which is just a program that itself is implemented with zeros and ones that the CPU understands. And those zeros and ones collectively know how to recognize keywords or functions in that source code language it takes as input in order to execute it on the program's behalf. So what is an example of an interpreted language? Well, among the most popular ones today is that called Python. Python is especially popular in the world of data science, in web programming, and in command line applications. One's written at the so-called terminal window via which I can solve problems. And so Python is notable too for its relative simplicity, certainly vis-a-vis something like C. In fact, in order to implement the equivalent program in Python that I just implemented in C, it suffices to write just this. Say what you mean and little more. There's less syntax here. There's fewer keywords that are unfamiliar. It's just instead the verb or function print followed by hello world. No semicolon, no curly braces, fewer symbols altogether. But how do I go about running a program in Python? Well, it turns out that typically Python is interpreted, not compiled. So I'm not going to run it through a compiler per se, but I'm instead going to interpret it line by line, albeit just one line with this particular program. So let me go back into my text editor and terminal window, and this time create a file called hello.py. .py being the conventional file extension for any program written in Python. And in hello.py, am I now going to write that one-line program? Print, open parenthesis, quote unquote, hello world. How now do I interpret this file called hello.py? Well, it turns out I run a program that itself is called Python, which is my interpreter. And so I run in my terminal window Python space hello.py, and the output is now the same. So what has just happened? Albeit just one line, what that program called Python has done is open up this file called hello.py, read it top to bottom, left to right, albeit quite quickly, recognized that it knows this keyword or function called print, and therefore knew what to do next. It went ahead and printed hello world on the screen, and then automatically quit. So this seems like a nice thing. No longer do I have to remember and take the time to compile my code, but surely there must be some price. And indeed, one of the implications of saving that step, no longer having to compile your code, but instead just jumping right to its execution or interpretation, is that you pay potentially a performance penalty. You certainly can't quite see it in a program as short as hello world, but if you were to write a program with hundreds or thousands or millions of lines, the overhead required to read that file top to bottom, left to right, and to figure out based on the instructions therein what it is the programmer intended actually does take non-zero amount of time. And it can surely add up for the most computationally complex of problems. Anything involving analysis, anything involving loops or cycles, you can certainly begin to feel its effects. But that's okay, because we humans have been fairly creative over time, and as we've invented more and more programming languages, we have fortunately also invented more and more solutions to problems like these. And so it turns out that even though this all happened quite quickly, when I ran this interpreter called Python, odds are, if my computer were smart, it was probably doing me a favor underneath the hood without my even knowing. And in fact, what Python and some other interpreters do is actually compile your code for you, save the results in a temporary file that you yourself might not even see, and the next time I run this program, especially if it's large and complex, Python will skip this step of reinterpreting the file again and again, and instead look at that pre-compiled version of my same program, therefore saving some time but achieving the same results. Only if I go back and change my code and make changes to my program does Python need to regenerate that cached version of code, if you will, in order to reuse that again and again. And this intermediately cached code is generally called bytecode. It's not quite zeros and ones, but it's closer to it than Python itself. And so for this same program in Python, were my computer to actually compile it for me, what I would actually see is code like this. Much like assembly code, is it fairly cryptic, but at least in there is some familiar phrase, hello world, as well as the function I ultimately called, which is that known as print. Now, Python and C are not the only languages out there. In fact, there are dozens in vogue these days, and there are hundreds, if not thousands, that humans have created over time. For instance, depicted here is perhaps one with which you yourself are familiar or have at least heard of. It's called Java, and it happens to be an object-oriented programming language, a language which means it has features beyond those earliest of ones like C. Here, though, is perhaps the simplest way via which you can implement that same program, Hello World, but it, not unlike C, has a bit of overhead. A number of symbols and words that at first glance certainly are non-obvious, but ultimately that's all this program does. But Java is distinct in that it took a different approach to another problem that we've not yet tripped over. I've been running this program thus far on my Mac, and I compiled it particularly for this Mac on an Intel CPU. But it certainly stands to reason that you or someone else might not have the same computer or operating system as I, and it would seem to be quite the burden on the programmer if they have to compile their code in a different way for you and for me and for everyone else. And so it turns out that this cost of doing business, if you will, shipping different shrink-wrap boxes back in the day of the same program for different computers and OSs, is ultimately solved by way of a virtual machine. A virtual machine, as the name implies, is not a physical machine, but a virtual one implemented, as they say, in software. Software that humans have written that mimics the behavior of a virtual imaginary machine. And then companies like Sun and others have implemented support for that virtual machine for Macs and for PCs and for multiple operating systems. And so Java subscribes to the mantra of write once, run anywhere. You needn't compile it again and again for different platforms. Rather, you can install on each platform its own virtual machine and run the exact same code. So this is simply a different approach to an otherwise omnipresent problem, but Java falls into a class of languages that uses that particular technique. And what other languages are out there? Well, very popular these days on both servers and clients is a language called JavaScript, such as that pictured here. Here is yet another language, this one called Ruby, that replaces the word print with just put, but it too is more syntactically simpler, much like Python itself is. On the other hand, here is C++, incredibly common still, especially on PCs, along with other languages as well. But in C++, you see code reminiscent of C itself, also conventionally compiled. Now, if you'd like to see any number of overwhelming examples of how you might quite simply, in hundreds of languages, say, hello world, take a look at this URL here. And in fact, there's so many other languages that are popular and powerful, sometimes in different ways. In fact, it's not just the case that you use one particular language for one particular job. There are many tools that you might bring to bear on the exact same problem at hand. In fact, the reason that so many languages exist is that over time, we humans have perhaps rightly or arrogantly decided that we can do better than languages past. And so humans invent new languages that have other features, different approaches. And of course, reasonable people can disagree, and so you have some languages that can achieve the very same task, they just do it differently. The text looks a little different, the features are a little bit different, and so it's up to the programmer as part of the design process to decide what tool is best for the job, not unlike a physical tool that you might have in a home tool chest. Among the most popular these days perhaps are these here: Bash and C and C++ and C#, Clojure and Erlang and F# and Go, Haskell, Java, JavaScript, Objective-C, OCaml, and then PHP, Python, R, Ruby, Scala, Scheme, SQL, Swift, and so many more. In fact, if you'd like to see a nearly exhaustive list of all of the language humans have invented, take a look at Wikipedia here, which goes into so much more detail. So suffice it to say that computers can print hello world, but they can do so much more as well. So what are the basic building blocks that can be found in languages like C, like Python, Java, C++, and any number of others? Well, let's return to the pseudocode with which we began to program, albeit verbally, some time ago. Here we had the algorithm via which to find Mike Smith in a phone book and to search more generally. Recall, though, that laced throughout this pseudocode, or program really, were a few constructs that were semantically distinct from each other. Let me go ahead and highlight in yellow some of the verbs that we saw last. Pick up and open to and look at, call, open and quit. All of these were calls to actions, verbs, or functions as we described them previously. Well, it turns out that in C and in Python and other languages as well, we have not necessarily these same words, but these same actions. For instance, we've seen in two languages already that you can print hello world on the screen. That function or verb in C happens to be called printf. In Python, it happens to be called more specifically print. And so those are examples of functions in those languages as well. What else did we see last time? Well, we had if and else if and else if and else, and we described these as conditions or branches via which you can make decisions and either go left or right down the fork in the road. Well, in Python and C and in other languages too, do we have those same features as well. We then looked at Boolean expressions, questions that you can ask to which there are yes and no or true and false answers. In Python and C, we're going to see those as well. And lastly, we saw loops. Go back to step 2, go back to step 2, a programming construct via which you can do something again and again. Now here we did this in order to keep looking for Mike, but in the real world, might you be searching for data in a large database or an Excel file, a CSV file, comma-separated values, and so you might want to have some programming code that opens that file and then iterates or loops over one line after another. Doing some calculation or analysis, loops enable us to do exactly that. So let's go ahead now and see if we can see these constructs in a common modern programming language. We'll use Python, if only because it's incredibly commonly used at the command line within a terminal window. It's incredibly commonly used nowadays for web programming, and it's ultimately incredibly useful in the context of data analysis and data science more generally. So let's begin where we left off, recreating a program in Python that quite simply says, hello world. To do that, in my text editor here, I've created a file now called hello0.py to suggest that we're going to do this a few times starting at 0 in order to iteratively improve on this program. Well, herein I'm going to do print, quote unquote, hello world. Saving my file, no need to compile it, but I'm now going to go ahead and type Python space hello0.py. And there we have hello world. Now this program, of course, is by definition not terribly dynamic. No matter how many times I run this program, it's going to print hello world again and again. Suppose that I instead wanted to get user input. Well, it turns out that Python, like other languages, has a function via which you can do exactly that. And a function, of course, takes optionally input and optionally produces some output. Now in Python, perhaps the easiest function with which to get users' input is called quite simply input. So let's see how we might use that. Let me go ahead and create a new file called hello1.py. And in this file, am I first going to call that function called input. And input is called exactly that, but it takes as input some input, which is to say the string or the phrase, the sentence via which you want to prompt the human for his or her input. So for instance, I'll go ahead here and ask, what is your name? Question mark space. And now this function is going to return to me a value, so to speak. I don't know how input is implemented. Someone else yesteryear implemented this for me. But I do know per its documentation that when I call it, it's going to do the equivalent of handing me back a slip of paper on which is written the user's input from his or her keyboard. But for me to make use of this input, I need to store it somewhere. And in a programming language, much like in math, you have access to what are called variables. Now, a mathematician might call their variables x or y or z. And in programming, could we also call our variables the same? But more conventional is to use names that are a little more descriptive, actual words that describe their contents. And the means by which I can store the return value, so to speak, what is handed back from a function like input, is in a variable that I'll call, perhaps aptly, name. And in order to store the return value of input into a variable called name, it suffices simply to use a single equal sign. And this equal sign is not to be confused with the equal sign that you and I know in math. After all, in math, using an equal sign would imply that what is on the left equals what is on the right. And ultimately, that's our goal. But initially, we only know the value on the right, the so-called return value from input that's handed back to me, so to speak, from the function. So in fact, what the equal sign in many programming languages is called, Python among them, is the so-called assignment operator. And so you consider what's happening here as being this. On the right-hand side is a function. It's handing back some value, the user's name. The equal sign implies copy that value from right to left into whatever's on the left. And so if on the left I have a variable called name, that variable, much like x or y or z, is going to store the user's input ultimately. So I can use it subsequently in some other line of code. Now what might that subsequent line of code be? Well, suppose I'd like to print not just hello world, but hello David or hello someone else. Well, now I can simply structure the second line as taking as input the contents of that variable. So I might go ahead here and say print, quote unquote, hello, comma, and I now somehow need to append append to that shorter phrase the name that has actually been typed in. And there's a number of ways we can do this. For instance, we might do it as follows. It turns out in Python that you can use plus not only to add two numbers together, but also in some sense to add two words, or two strings, as they're called in a language. And if I do plus in between hello and that variable name, the effect is going to be to join or to concatenate those two strings of text together, so that what ultimately is printed is hopefully hello, comma, David, or hello, comma, yourself. So let me go ahead and save this file, and in my terminal window now, run Python of hello1.py. I'll input my name, David, and now notice my input is separated by one space from that question mark because on line 1 did I preemptively include that space between those double quotes. Now I'm going to go ahead and hit enter, the effect of which is to have input return that value, storing it in the variable called name, and then in line 2 does print go ahead and print hello, comma, followed by name. Now, just to be clear that this is not hard-coded somewhere else, let me go ahead and run it one more time, Python hello1.py, and let's go ahead and type your name. And there too, do we see hello, your name. So the program is now dynamic, and I've outputted dynamically whatever it is the human has typed in, but it turns out there's any number of other ways we can do this. And so just so that we've seen a few different ways, let me go ahead and create a new file called hello2.py, wherein we have almost the same code, but we're displaying your name or mine a little bit differently. As before, I'll go ahead and define my variable called name, assign to it the return value of input, asking the user for his or her name. And then on my second line of code, well, again, go ahead and say print, hello, comma, and then following that, I actually have a choice. I don't necessarily have to just concatenate one input onto that first string hello. I can actually combine these as two separate inputs to print. It turns out that print, like many functions, can take either 0 or 1 or 2 or any number of inputs. You simply, as the programmer, need to separate them by commas. Not the comma that's inside of the quotes. That's just my English grammar separating hello from your name. But outside of the quotes, and so my text editor is displaying it a little bit disparately in white. So in this case, am I using the same function print, passing in not one but two arguments or inputs, the second of which is that actual name. Now there's a minor bug here that I'm not yet anticipating, but let's see what happens next. If I go ahead now and run Python hello2.py, type in my name, voila, it's so close and almost right. But here perhaps is my first bug. It's not necessarily a bug that's breaking the program altogether, but to be a little bit nitpicky, I think we could do a little bit better, say, grammatically. There seems to be two spaces instead of one. But where are they coming from? Well, it turns out that functions, when they take inputs, can also have default behavior. And in this case, print is designed by its authors, whenever you pass in two or more arguments, to just separate them by default with one space. Now, I can fix this mistake in a couple of ways, but the simplest way is just to remove it from my own input. Saving the file again and rerunning Python of hello2.py gives me now, what is your name? David. And we're back to hello, comma, David. Now, it turns out there's yet more ways than you can format information on the screen. And just so that we've seen one other way, allow me to create a fourth file called hello3.py. In hello3.py, am I going to start almost exactly the same, declaring a variable called name, assigning to it the return value of input, asking the user for their name, and then in my second line of code, am I again going to use print, starting with a parenthesis and a close parenthesis. In there, am I ultimately going to say hello, comma, something? And the something this time is literally going to be name, but not quite name on its own. Indeed, if I were to run this program now, what do you think might be printed? I've said to the program, print hello, comma, name. But unfortunately, name is as written, N-A-M-E. And so I would literally see that on the screen no matter what I typed in. But it turns out in Python, if you surround your variable's name with curly braces, typically found just above the Enter key, at least on a US keyboard, you can tell Python that this N-A-M-E is actually the name of a variable, not just a string of text on its own. But in order to tell Python that it should treat this string, this input to print, a little bit differently than usual, you have to fairly cryptically prefix it with a single F. thereby telling Python that this is what should be called a format string or F string. That is a string of text, a sequence of characters that should be treated as formatted in a special way. And according to Python's own documentation, if you format your input using these curly braces inside of which is the name of a variable, Python will go through the trouble of plugging in the value of that variable there and therefore formatting it for you. And so I'll again go ahead and run Python of hello3.py, input my name, and voila, we're back to hello David. So what are the takeaways then from these simplest of programs? Well, we clearly have the ability to print information on the screen, but we have at our disposal a function, a piece of code that someone wrote long before me that takes as input perhaps just a string like hello world. But if you pass it multiple strings, will it handle those as well? And if you pass it a special type of string, will it handle that as well too? And so depending on the documentation for some language, do you have these and so many more features available to you? And so one of the first steps in learning any programming language is not to take a formal lesson or class, but simply, quite honestly, to read the documentation. And once you have under your belt some knowledge of one or two or few programming languages, is it much easier in the computer world to pick up new ones than I dare say it is in the human world, where you have a much larger vocabulary at hand. All right, enough about printing. What more can we do? Well, programming languages can typically handle any number of arithmetic or mathematical operations, addition and subtraction, and many others among them. So why don't we go ahead and create a program that quite simply prompts the user not just for their name or a string, but rather two inputs, two numbers, and we'll call them more familiarly x and y. I'm going to go ahead and declare a variable called x, assign to it from right to left the result of asking for the user's input of x. And then I'm going to go ahead and do precisely the same thing on another line of code, defining a variable called y and assigning to it from right to left the return value of another call or invocation of input, this time prompting the user for y. And then I quite simply am going to go ahead and print out the result. So print x plus y, this time not using any double quotes at all, because what I literally want to print is x plus y, not the concatenation of two strings, not a string at all, but rather just a number. In my terminal window now, will I go ahead and run Python on the name of this file, arithmetic.py. I'm prompted for x, which I'll say 1. I'm prompted for y, so I'll say 2. And indeed, 1 plus 2 is 12. But no, 1 plus 2 is not 12. So what's actually happened here? Well, this is the first real bug, if you will, that I've introduced to my code. Now, step 1 here has x equals input, prompting the user for x, and step 2 has y equals input, prompting the user for y. A little different from before, though we've chosen different variable names. Now on line 4, and I've separated it with this blank space just to make it a bit easier to read, do I have print x plus y? But 1 plus 1 is surely not 12, but what appears to be happening? Well, it's no coincidence that the answer Python's giving me is my first input followed by my second. It would seem, in fact, that Python is concatenating my first input to my second, that is joining them, just like hello, comma, David. So why is that happening? Well, I would hope that plus, when given two numbers, would in fact add those two together, but here's a catch. It turns out that underneath the hood, Python, like many languages, actually has what are called types or data types. That is to say, different ways of representing information if that information is a number, like an integer, or even a real number with a decimal point, or a string of text, that is a sequence of characters, or maybe more generally a value like true or false, a so-called Boolean value, and even others still. And in this case, indeed, it turns out, and you would only know this by trial and error, by having read the documentation first, does the input function built into Python return to you not a number, but a string. Even though what I typed on my keyboard looks like a number and surely is in practice, it's actually not being stored as such by Python. It's being stored instead in such a way that the computer is interpreting it as a string of text. So we have to be ever more explicit. And indeed, computers don't necessarily know what I intend. Maybe the goal at hand was to write a program that concatenates one number against another. And so if I really want the user's input to be treated as numbers, I somehow have to coerce it to such or convert it, or more technically, to cast it from string to an int. Now it turns out Python has other functions with which I can fix this mistake, and I might do this in between these lines here. X should not just be whatever the user typed in. I want X to be the result of converting whatever the human typed in into the integer or int version of that string. Meanwhile, can I fix y by the same? Y equals int of y. Thereby telling Python, even though, yes, the human typed something in at a keyboard, therefore implying a string, go ahead and convert that 1 and that 2 to an actual integer underneath the hood. A pattern of bits, if you will, that represents not the ASCII value or the Unicode value that the user typed in, but the underlying pattern of bits that represents 1 and represents 2. Let's go ahead now and rerun this file as Python arithmetic.py. Inputting again 1, inputting again 2, and lastly hitting enter. And this time we have 3. Unfortunately, we've paid a bit of a price, albeit just a matter of style. I seem to have increased the length of this program from just 3 lines to 5 just to fix a simple mistake. But it turns out that just as functions take input and produce outputs, so can you pipeline them, so to speak, or nest them so that one function's output is another function's input. The result of which is that we can kind of tighten this up. I can instead, on line 2 here, delete what I have, and on line 1 alone simply say that once I get back the return value of input, the user's input, if you will, written on a conceptual sheet of paper, go ahead and pass it immediately to that function called int, and surround the whole thing with parentheses, thereby passing the output of input into the input of int, and then assigning the result from right to left. And again here, can I get rid of line 3, passing the output of this input to the input of this int, and again surrounding it with parentheses in order to pass its output into its input, ultimately assigning from right to left that value. Let's, to be sure, go ahead and save this file, and then in my terminal window, run one final time, Python of arithmetic.py, inputting 1, inputting 2, and still do we get 3. Suppose, though, that we not only want to take a user's input, but make a decision based on it, taking out for a spin this notion of a condition with some Boolean expressions. How might we do that? Well, let me go ahead and create here a file called conditions.py, inside of which I'm again going to ask the user for 2 inputs, call it x and y, and then I'd like to determine whether x is less than y, greater than y, or exactly the same. Well, as before, I can declare my variable called x, assign to it, preemptively this time, the result of passing to int, the return value of input, asking the user for just x. And then define another variable called y, assigning to it the return value of int, which is passed in turn the return value of input, asking the user for y. And now with these 2 numbers in hand, am I going to proceed to do the following. If x is less than y, followed by a colon, indented below that, I'm going to say quite simply, well, you know what, x is less than y, simply to inform the user as much. And then back aligned with the if, am I going to say, else if x is greater than y, with a colon, and then indented below that, print x is greater than y. Now, those are the semantics that I intend, but it turns out you have to read the fine print. In Python, it is not else if that you can use. Humans some years ago decided that slightly more succinct than else if would be literally elif, and that, in fact, is the correct syntax to use when you have a second fork here in the road. But indeed, when we have now a third, we might do this. Else if, oh, there I go again, elif x equals y, let me go ahead and say print x equals y. But there's a bug here already, because equal does not mean what you think. Indeed, before we've been using the equal sign as the assignment operator, so to speak, copying from right to left some value. And in fact, here on line 8, there's already a bug. Using a single equal sign between my x and y here would have the effect not of comparing those 2 values, but instead copying from right to left that value in y into that value for x, thereby making them equal no matter what. And so it turns out that we humans painted ourselves into a bit of a corner some years ago. We've already used equal to assign one thing to another. So it turns out that humans in many languages decided, well, let's still use equal, but 2 of them back to back. And so if you want to use not the assignment operator, but the equality operator, you want to use 2 of these things back to back. And so now I have a program that asks quite simply, if x less than y, print as much. If x greater than y, print as much then. If x equals y, print the same. X equals y. But we don't necessarily need this third condition, it turns out, right? Logically, if you've got two numbers, two integers, I'm pretty sure by definition it'll either be greater than one, less than the other, or exactly the same. And so we can save a tiny bit of time here by not even asking that third question. If I know that x is not less than y, and I know that x is not greater than y, I might as well just confer logically that they must be actually equal. And so here we have the first of my Python programs that, much like my pseudocode for finding Mike Smith, allows me to take users' input and then compare it in order to take a different fork in the road based on its value. So my Boolean expressions here are x less than y and x greater than y, and that's it. And my conditions here, or the syntax with which I induce these branches, are my if, my elif, and my else. But important in Python, unlike in pseudocode, is some of this syntax. The colon very specifically say, do the following if this is true. And the indentation, the multiple spaces, here I typed 4, is ever so important as well. Whereas many programming languages are a bit loose when it comes to white space, so to speak, how many times you hit the space bar or tab. Python enforces that you have the same amount of indentation everywhere. And so if I want lines 4 and 6 and 8 here to all line up logically, they must literally do so in the file. Similarly, must lines 5 and 7 and 9 line up just right so that they are only executed if the lines just above them are true. Let me go ahead and save this file, and in my terminal window, run Python of conditions.py, typing in, shall we say, 1 for x, 2 for y, and indeed x is less than y. Let's run it again, this time flipping things around. X is 2, y is 1, and indeed x is greater than y. And one third time, which it should be inferred, if x is 1 and y is 1, then indeed x equals y. Now, programming is not all about numbers. In fact, pictured here in a program I wrote already is answer.py, wherein we have lines of code that again prompt the user for input, but this time leave it as a string. And so on line 4, am I asking the user for his or her answer to a yes or no question? Presumably the user might type little y or little n, or perhaps capital Y or capital N. And indeed, I'd like this program to handle any number of those cases, as any program might. On line 7 here, am I asking then two possible questions? If C, the name of the variable I gave to the user's input, equals capital Y, or to be robust, that variable C equals lowercase y, let me go ahead and conclude and print that the user meant yes. Meanwhile, if C equals n capitalized, or if C equals n lowercase, similarly do I want to conclude that the user meant no. And so here, the new operative word is quite literally or. In Python, it tends to be fairly English-like, ever more so than C in other languages, where if you want to do something or something else, you literally say quite simply or. If I wanted both situations to be true, albeit illogically, could I use the actual word and? But of course, the user's input can't simultaneously be capital Y or lowercase y, and so here is using or apt. Now, when programming, you don't have to use only those functions that are handed to you by the particular language. You yourself can invent functions of your own. For instance, let me go ahead and in a file called return.py, implement a program that takes as input an integer or number from the user and then quite simply prints out the square thereof. So if the human types in 2, I'll print out 4. If the human types in 3, I'll print out 9. And so how might we go about doing this? Well, perhaps in a familiar way now. X shall equal the result of converting to an integer whatever the user's input is after prompting them for x. And then I'm going to go ahead quite simply and print out, well, x times x, that is the square of x. I'll go ahead and save this, and in my terminal window, run Python on return.py, and as proposed, square 2. And as proposed, square 3. And indeed, this program works exactly like this. But to square a value has kind of a nice ring to it. And the fact that it happens to be implemented as x times x is really just a mathematical implementation detail. Something that I shouldn't really have to worry about or remember. I would just like to square the user's input. So wouldn't it be nice if there were a function in Python, or any language for that matter, quite simply called square? Indeed, I can make that happen whether or not it exists and simply define it myself. And so here I'm going to go and do the following. Using Python's keyword called def, short for define, I'm going to go ahead and define a function called square. I'm going to specify to Python that that new function shall take input that I'll arbitrarily but conventionally call n for number, and then with a colon as before and some indentation too, am I going to go ahead and return, quite simply, n times n. In other words, the math is the same, the implementation details are the same, but what's new here is this new keyword return. Just like with the input function built into Python, some human in that function's own implementation had a line of code that said return to the user whatever they have typed in. Here I'm doing the same, but returning not some user's input, but rather n times n. And so you can think of this function called square much like that input function, jotting down on a digital piece of paper that value, handing it back to the caller or whoever uses this function, and letting them use it as they see fit. So now, rather than use x times x myself, can I more conceptually clearly say square of the user's input x. And the fact that x is not the same as n is quite OK. It is this function square that presumes to call its own input n. I can call my own input to square whatever I want, say x. So let's go ahead now and run this program and see what happens. Based on these definitions, it would seem that I could square x in this way. If I go ahead and run this program again, Python return.py, and type 2, I get more output than I surely intended. In fact, this is the first of my truly bad mistakes. Here do I see what's called traceback, which is sort of a trace or a log of everything the computer tried to do. And you'll see some hints, however arcane this output, that line 2 is where my mistake probably is. In particular, I have some kind of name error in Python where the name square is not defined. And yet it's right here. Well, it turns out that Python and a lot of languages take things fairly literally. And if when interpreting your file, they're reading top to bottom, left to right, unfortunately, it's too late to define square on line 4 if you yourself want to use it on line 2. But we could surely fix this logically, as by moving that code up top, down below, defining square at the top, writing my own logic below, now trusting that Python will see square and only use it on line 5. Let's go ahead and save this file, rerunning Python of return.py, again typing 2, and voila, now it works. But this isn't quite the most conventional way to solve this problem. As naive as Python is, reading your code top to bottom, it's a bit of a regression now, a bit of a mistake, that I'm putting the actual code that I care about at the bottom and the actual code that I was trying to abstract away, if you will, and give name to at the very top. At the end of this day, the program I care about are these lines here, not my implementation of square. And so I would actually prefer, albeit a bit nitpickily, to put that code actually where it was. And so if you do that, thereby keeping the main part of your program at the top, as is convention, you still have to solve the same problem. So how might we do that? Well, the Pythonic way, or the conventional way in Python, is to do this. To define a function that most people call itself main, again ending it with a colon, indenting below that the lines you have written, and then at the bottom of the file, as the very last thing you do, telling Python to call that function called main. Because here now is what Python will do. It will read this file and interpreting it top to bottom, left to right, defining a function called main, and then here, defining a function called square, and then here, calling one of those two functions, which in turn calls the second. But in this way, have you taken care to define all of your functions first and never calling any of them until everything's been defined. Now, so that you've seen it too, it's not quite conventional to just run main at the bottom. Instead, you'll typically see a more magical incantation like this. If underscore underscore name underscore underscore equals equals quote unquote underscore underscore main underscore underscore colon, indented below that will be your actual call to main. This, for more arcane reasons, ensures that if you're using a small program as part of a bigger one, it won't necessarily get executed at the wrong time. But logically, what the key takeaways here are what you can actually do by defining your own functions. Here too do we have an abstraction. What does it mean to square two values? Simply multiplying one against the other. But it would be nice to just refer to that as a verb unto itself, like square. And so by defining this function, do we now abstract away that multiplication and just treat this as the idea we actually care about? Now, of course, we're not saving all that much time, and my program's even bigger than it need be, but it's demonstrative of this principle of abstracting away implementation details and building your more interesting product on top of work that you or someone else has already done. Now, what if we want to do more than just square a number? We instead want to prompt the user for input, convert that input to a number, and then ensure that that number is the type of number we want. Indeed, it's not uncommon in a program to ask the user for a positive integer, something useful, again and again until he or she provides just that. For instance, the user might type 0 or negative or something else still, but you want to pester them again and again until they provide exactly the input you expect. Much like in a website where you're forced to type a number or email address or something else. Similarly, can we do that in Python in code? So let's go ahead and do exactly that and assume for the moment that there exists already a function called, say, getPositiveInt, a function whose purpose in life is to get from the human an integer from 1 on up. Let me go ahead and preemptively this time define my own main function with def. And inside of that code, go ahead and declare a variable called I for integer, and then just presume for the moment to call a function called getPositiveInt, which itself will take a prompt as before, asking the user, say, for I. And what do I want to now do with this number? Well, let's keep it simple for now and just print I itself. But I now need to implement that function called getPositiveInt. So for that, I can use def and say def getPositiveInt, but I need this function to take itself a prompt, and I'm going to go ahead and call it exactly that, which is to say when I call this function, as I've done on line 2, passing in some string of text that I want the user to see, well, in my definition of getPositiveInt on line 5, I need to tell Python to give that input a name so I can refer to it ultimately. Because indeed, what I'm going to do after adding that colon and indenting underneath is ultimately want to call input passing in precisely that prompt. After all, getPositiveInt is not going to presume to know in advance what the programmer wants to prompt the user with. Instead, it's going to get it just in time via that input or argument. But I need to pester the user again and again if they don't actually give me a positive int. And so how might I do that? Well, just like in pseudocode, we might define for ourselves loops, blocks of code that do something again and again as we go to step 2 as before. So can I do that in Python, and in any number of ways, but perhaps the simplest here is this. To simply say, you know what, Python, go ahead and give me an infinite loop while true. While being my operative word here, inducing a loop while something is true. Well, you know what's true always is the word true. And indeed, built into Python are Boolean values, true and false literally. By definition, capital T, capital F. So by saying while true colon, I'm saying Python, please go ahead and do something again and again until I tell you to stop. Well, what do you want Python to do in this loop? I want to go ahead and declare a variable called say n, assign to it the return value of calling that int function, passing to it the output of input, and then and only then, if the human has obliged and given me a positive int, I'll go ahead and say, well, if n greater than 0, go ahead and break out of this loop. So a different approach than we saw in pseudocode where I simply said go to and go to and go to again. Here I've instead said Python do this forever until I say break. And only once n is greater than 0 as per the user's input do I break out of this loop entirely and therefore return when I'm ready that value called n. And so here on my last line of code, am I again using return, handing back, if you will, a sheet of paper on which is that number, but I only reach this line 10 after I've said break on line 9, and so does this function getPositiveInt ultimately return exactly that. So as always, let me go ahead now and save this file, but only after adding that last cryptic line. If the name of this file is implicitly underscore main, then do I want to go ahead and call main so that we avoid all of those issues of code in the wrong order. I'll go ahead and click save and do Python of positive.py, providing an input, say -1. Being prompted again for a number, so -2. Still not a positive int, nor is 0, but if I finally type a value like 1, do I actually see the one that I inputted. But it turns out Python supports other types of loops as well, not just via this keyword called while, but actually via a preposition called for. For instance, suppose that I want to implement a program that, not unlike a charting program like Excel, prints for me some kind of bar chart. These bar charts will be purely textual using, say, hash marks to represent values. But to do this, I'm going to have to prompt the user for input and then print out precisely that many hashes horizontally. Well, let's see what I get. I'm going to go ahead and, as always, prompt the user for input. We'll call it, say, n. And that user's input shall be converted via int, after asking them for that, value of n. And then once I have that value, do I want to iterate, that is loop, some number of times equal to whatever the user's input was. So if the user has inputted 1, I'll print just 1 hash mark. If the user inputs 10, I want to print 10 of those hashes. But how do I do this? A while true loop or forever loop that infinitely loops is probably not the right approach here, but rather I want to iterate some finite number of times. And so a for loop allows us to do exactly that with built-in functionality as follows. Let me go ahead and say Python for I in the range of n, which is the user's input. Go ahead per the colon and do the following next. Go ahead and print out a single hash for each value. And so what is this line of code doing? Here on line 3, do I have for I in the range of n? Well, it turns out that range is a function built into Python that returns to you effectively a range of values. By default, that range starts at 0 and goes up to, but not through, the value you ask for. So if you pass to range the value like 1, you will iterate only one time, the range of 0 to, but not through 1. If you instead input a value of 10, you'll iterate over a range of 0 through 9 up to, but not through 10, and get precisely that many hashes. My goal, again, is to print a bar chart of sorts with 1 hash representing each of these values from left to right, a horizontal bar chart. So let me go ahead and save this file here, and in my terminal window, run Python of score.py. We'll input a number like 10, and unfortunately, they all seem to be vertical. And if I scrolled up higher in my terminal window, would I see all 10, but again, one on top of the other? So how do I somehow keep my cursor, if you will, on the same line? Well, all this time I've been using print, I've been getting a new line for free, so to speak. At the end of printing anything, has Python been moving my cursor, not unlike an old school typewriter, to the bottom left of the next line. But sometimes I want my cursor to stay on the same line even as I do something again and again. And it turns out Python, and you only know this by having looked at the documentation therefore, is that the print function can take a second input that is not necessarily just some other string you want to print, but instead it's a named parameter. That is an input that has a predetermined name, in this case called n, that you can set equal to a specific value like nothing. It turns out, albeit non-obviously, that by default, Python ends each line with a carriage return, if you will, or a blank line, otherwise represented here technically as a \n, which itself is technically distinct from an old school carriage return, but has the effect of moving that cursor down to the next line. So this is implicit. It would be incredibly annoying if any time you wrote Python code and wanted to print something that you had to type out that sequence of symbols. And so you get those for free, so to speak, but if you want to override that default behavior, you need to instead tell Python's print function, you know what, end your lines with nothing at all, quote unquote, with nothing in between. But when I'm done printing all of them, it would be nice to move my cursor to the next line so that my next prompt, that $sign we keep seeing in my terminal window, is at least on its own. So I'm going to go ahead and say print open paren, close paren, with nothing inside that, because if I get for free a blank line, I don't need to pass anything to print. That is, as the very last step, just going to move my cursor to the next line. So let me go ahead and save this program now, and again in my terminal window, run Python of score.py, typing in this time 10, and there do I get my 10 hashes horizontally. So it turns out Python has what are called types. And the only time you really need to know or care about this is when, frankly, it starts to bite you like it did us. Indeed, when I asked for the user's input and expecting an integer, but the user typed exactly that, but I didn't convert it in advance to an int, I got ultimately that weird behavior of concatenating one string to another. So underneath the hood, are there any number of types built into Python? A bool like true, false, integers like numbers, strs or strings of text, and even floats, real numbers that have a decimal point and some number of digits after. But beyond that are more sophisticated data types or data structures still. Dict or dictionary, which is, as we'll call it, a hash table of sorts. List, which can be any number of values back to back. A range of values, as we've just seen, or a set wherein you have no duplicate values. And a tuple, not unlike x comma y or latitude comma longitude. But it turns out that an appreciation of these types can help you avoid some very serious mistakes in code. Because it turns out that depending on how you store your data in a computer's memory, you might actually get behavior that you didn't actually intend. For instance, let me quite simply write a program that prints out the value of, say 1 divided by 10. I have here a file called, say, imprecision.py that I quite simply am going to do this. Prompt the user for an input called x, converting their input to an int as always, asking for x, and then defining another variable called y, this time converting to an integer the user's input after prompting for y. And then quite simply, I'm going to print x divided by y. Let me go ahead and save this, and in my terminal window, run Python of imprecision.py, hitting enter here, typing in, say, 1 divided by 10. And so 0.1 is the answer, just as you'd expect. Let's go ahead and print out more digits than 1 after that decimal point, just to make sure that 1/10 is indeed 0.1 with implicitly an infinite number of zeros to the right. Well, let me go ahead, just for simplicity's sake, and first store the value x divided by y in a third variable z. And then in my print statement here, let me print out exactly that z, but let me format it a bit differently than usual. Using Python support for an f or format string, using that prefix f, which connotes give me a format string, am I going to print exactly that? Quote unquote z. But recall that you need to surround it with those so-called curly braces to make clear to Python that you want to plug in its value and not literally z. Well, it turns out there's additional syntax we can use, albeit cryptic, via which to tell Python, yes, print z, but to this many decimal places. And the syntax for that is a colon right after the variable, followed by a literal period, and the number of decimal points that you'd like to print. And because this is a so-called floating point value or real number, we need one additional f. Now, with this syntax, should I be able to print that same value, but to a specific number of decimal places? Let's see. In my terminal window, let me go ahead and run Python on imprecision.py, again inputting 1, again inputting 10, and phew, I indeed see 0.1 followed by 9 more zeros, a total of 10 digits. Well, let me get a little more curious and instead print out, shall we say 20 decimal places. Again, running my program, imprecision.py, inputting 1 followed by 10, and all looks almost good until, wow, 555. I'm a little curious now as to what's going on. Let me go ahead and run this one last time after saying printing 30 decimal places. Here I'm going to go ahead and run Python of imprecision.py, hoping that the problem's not going to get worse, and it does. It seems if you look far enough out, you start to see some weirdness. In fact, let me go as far out as, I don't know, 55 decimal places, going ahead and running Python of imprecision.py and putting 1 and 10, and oh my god, it does get worse. So it would seem that all of us taught in grade school that 1 divided by 10 indeed equals 1/10 is not quite true. If you look far enough beyond the decimal point, eventually things go horribly, horribly awry. And that is because computers, quite often, as powerful and as sophisticated as they are, can't quite do everything and can't quite do everything that we humans do. Now, why is this? It would seem that Python is ever so slightly off when it comes to the representation of this floating point or this real value. Now, why is that? Well, inside of a computer is hardware like this, RAM, or random access memory, which is a little chip of memory inside of your computer wherein files and programs are stored when they're open or running. And inside of each of these black chips is some number of bytes or bits that are ultimately used to represent any of the values in your program. The catch here, though, is that this device, like any physical device in the real world, has only a finite amount of space or capacity, which is to say, no matter how big or expensive this particular RAM is, it has a finite number of bytes. Maybe 1 billion if it's a gigabyte, or 2 billion if it's 2 gigs, but it's a finite number in total. And by default, what Python and most languages do is they decide a priori how many bits or bytes to use to represent any of the values in your program. And so if your number is so precise or so big that it can't quite be represented in only that many bits, the language, like Python, is going to come as close as it can and represent that value with some approximation. And that's what we're seeing. 1 divided by 10 is surely a mathematically well-defined number. Indeed, it's 1/10. Or 0.1, and mathematically should be 0.10000 ad nauseum infinitely. But in Python, if you're only using, say, 32 or 64 or any number of bits, you can't possibly represent the infinite number of numbers that exist in the world and represent all of them perfectly precisely. To do so, you would surely need an infinite number of bits, and we don't have that in our physical world. And so you have to suffer, unfortunately, this potential for floating point imprecision, where values you care about are going to be close but not quite what you intend, unless you, the programmer or designer of the system, are willing to spend more than just 32 or 64 bits, but more and more and more, and enough that you can get that decimal point and those values as far off to the right, so to speak, as you can. But darn it, if there isn't another problem that derives from precisely the same constraint. Not only can you have imprecision when it comes to floating point values, even integers are potentially flawed. Not necessarily in Python, because in the latest version of Python, have they designed in the language the ability to use as many bits as you need to represent integers, specifically. Numbers like -1 and 0 and 1 and everything to the left and everything to the right. The language itself will use more and more bits to store exactly the integer you want. But that did not used to be the case in Python, and is still not the case in some languages. Some languages are vulnerable to what's called integer overflow, whereby if in that language you try to count so high that you need to represent a number that's too big to fit in the amount of storage you've allocated, 32 or 64 or some number of other bits, you're going to overflow the value. The result of which is that you might be going up and up and up and up and representing a bigger and bigger value, but it gets so big that all of the ones in that number become zeros, and somehow accidentally you end up overflowing and starting all over numerically. Now, how might that be? Well, consider a number that's represented with only 3 digits. And let's start counting, for instance, from 123. Adding 1 to that gives you 124, followed by 125, 126, 127, 128, 129. And what do we do in our human mathematical world? Well, if you're about to hit 9 and we now need to go to 10, you don't just write 10, rather you write 0 and you carry the 1, so to speak. Continuing now with your logic, adding that 1 to that 2, giving you 130. And that's okay. We've stayed within the confines of that 3-digit number. But of course, if we go count up long enough, we'll eventually reach 999. But if we have decided to only allocate 3 digits for this number, where or what is going to happen when we add one number to this? Well, you might be inclined to carry the 1 and carry the 1 again. And in the human world where you have the luxury of pen and paper, you might simply write down 1000, which is the right value. But if your computer or device is only representing values with 3 digits, you have overflowed this particular value. And you've overflowed it in the sense that even though I have it here on the screen, that doesn't actually have room in which to fit. And so your number 1000 becomes mistaken for 000, thereby having you overflowed and wrapped around from a big number to a small. Now, you might think that this is fairly contrived, and why would you ever do something so foolish as to only represent numbers with 3 digits? Well, we humans have done worse. Now, it wasn't all that long ago that we humans made precisely this mistake, using just 2 digits to store years. After all, if almost all of your dates start with 1900 something, you might as well just store those last 2 digits. Unfortunately, by December 31st, 1999, were many of us quite a bit nervous that we hadn't found all of the code and all of the devices in the world that were still using just 2 digits. Because as with integer overflow, if you have a number already counted up to 99 and you only have 2 digits, you might run the risk that 99 rolls over, overflowing to 00, and all of a sudden it is not the year 2000, but 1900 again. Quite simply the result of integer overflow by using a fixed amount of memory to represent something and not having anticipated that you might eventually need more. But you can certainly design for this and engineer defenses against this. Indeed, some games have done better than we as a society. Indeed, this game here, Lego Star Wars, has a point system wherein you can accumulate coins over time. And if you play this game long enough, you can accumulate apparently as many as 4 billion of these coins, but unfortunately, no more. Because the engineers who designed this game decided that the maximum number of points you can accrue is just that, 4 billion. But why? Well, it turns out that in many computers and game consoles, it's conventional to store your integers, or ints, as 32-bit values. 32 zeros or ones back to back, which means you have 2 to the 32 possible permutations thereof, which means you have roughly 4 billion possible values. You actually have a few more than 4 billion, but it's perhaps cleaner in a game to just choose a clean value with lots of zeros. But in this game, did they anticipate that you play this game too long and you might eventually overflow, and who knows what might happen to that gamer if he or she plays the game so long and all of a sudden their high score becomes 0. So these problems are solvable. You just have to anticipate and actually engineer those solutions. But sometimes we don't, including companies like Boeing. It wasn't all that long ago that the Boeing 747 had a software bug in it whereby the plane's power system might actually turn off while the plane, in the worst case, were actually flying. One article put it as follows. A Model 787 airplane that has been powered continuously for 248 days can lose all alternating current, AC electrical power, due to the generator control units, GCUs, simultaneously going into fail-safe mode, the memo stated. This condition is caused by the software counter internal to the GCUs that will overflow after 248 days of continuous power. Boeing is in the process of developing a GCU software upgrade that will remedy the unsafe condition. Another website analyzed the situation as follows. A simple guess suggests that the problem is a signed 32-bit overflow, as 2 to the 31st power is the number of seconds in 248 days multiplied by 100. That is a counter in hundredths of second. Which is to say, it is presumed that Boeing had stored some form of integer in its own software. And that integer was representing the number of hundredths of seconds for which the power had been on. But if you're only using 32 bits and only have at your disposal roughly 4 billion 100ths of seconds, turns out mathematically after 248 days, that counter, which is clearly important, might overflow and wrap around to 0. The result of which is that the power of an airplane might shut off. And so the temporary workaround before the software upgrade was deployed was to quite literally reboot the airplane while on the ground before that 248th day. Now, we've only just scratched the surface of what you could do with Python. And in fact, we've looked at some of those characteristics that are demonstrative of the features that you might find in any number of programming languages. But we're not even limited to the functions that come built into the core language itself. It turns out there are called libraries and frameworks and yet more in any number of languages that provide additional features that you somehow have to load or import manually in order to use. One such example might be in Python if you want to generate random, or technically pseudo-random numbers to create some kind of variation in how your program behaves. It turns out that you can't just call a random function right out of the box. You need to tell Python to please load or import that feature for you. So let's go ahead and write a program in a file called pseudorandom.py that allows us to generate a random number between, say, 1 and 10. I want to go ahead, though, first and do this. From a library called random, go ahead and import a function called randint for random int. And then if I want to go ahead and generate or select and then print a pseudo-random number between 1 and 10 inclusive, I can simply do print randint 1, 10. And the effect will be to let Python somehow figure out how to choose a number between those two values and return to me so that I can print it. Let's go ahead and save the file. And then in my terminal window, run Python of pseudorandom.py and 10. Let's go ahead and run it again, and this time I get 6. Let's go ahead and run it yet again, and this time I get 10. Yet again, let's go ahead and run it, and this time I get 1. And if I were to run it, shall we say, an infinite number of times over time, I would see a uniform distribution, hopefully, of those 10 possible values. And that's what's meant by pseudorandom itself. It turns out that languages and computers more generally can't really pick a random number off the top of their head like you and I can. Rather, they need to use algorithms, which themselves are deterministic processes, code that does the same thing again and again in order to create, if you will, the illusion of randomness by creating a statistically uniform distribution over some range of values. Now, often a computer will use something that's changing, like the clock that's built into it, taking a look at the current time and then generating a random number, or again, pseudo-random number based on that variation. Or if it has a microphone or a camera, taking some ambient noise of sorts and using that to feed into whatever algorithm it's using to choose something randomly. But suppose I want to now do something with this value and not just print it. Suppose that we want to implement a bit of a game for a user, pick a random number between 1 and 10 and see if they can guess it correctly. Well, let's see how a program like that might be implemented. Let's first go ahead and from that library called random, import as before a function called randint. Although it turns out if you want to use not only this function or others, you can more succinctly just say import random. The difference being if you only import random, we are going to have to prefix with the word random followed by a dot every use of a function. So we'll do it that way this time. Let's go ahead and declare a variable called n and assign to it right to left the result of calling randint. But this time, because we've not mentioned randint by name, I need to qualify this symbol and say random.randint, thereby making clear to Python that the function I'd like you to call is actually inside of that library called random. But I can otherwise use it as before, passing in two values, a lower and upper bound like this, 1, 10, and that should give me in n a random number in that range. Now I want to go ahead and ask the user for their guess, and I'll go ahead and define another variable called, say, guess, that is the result of converting to an int whatever the user's input is for their guess. And now, quite simply for this game, I want to compare those two values and print, say, correct or incorrect. And so I'll go ahead and say if the user's guess equals n, go ahead and print out as much correct. Else, if the user's guess is not right, let's implicitly infer that nope, incorrect, and so we'll print that instead. Let me go ahead and save this file now and run Python of guess.py. This time I'll be prompted for my guess. I'll say 5. Unfortunately, it's incorrect. Let's go ahead and play again, this time running Python guess.py. This time I'll go with 10 since we saw it so many times before. Incorrect. I'll run it a third time and see what's going on. This time I'll guess 1, but incorrect. Unfortunately, I've implemented perhaps the most frustrating game ever because I'm not even telling the user what the actual number was, but surely I could do that by printing the value of the variable I stored that random int in, but that would be yet another game altogether. All right, let's now bring all of this together and solve an actual problem, one, say, from yesteryear. You might recall this game here, Super Mario Brothers, the original, and this was a two-dimensional world built up of images like this. Well, there in the sky, so to speak, do I see 4 question marks, and that seems like an opportunity to do something again and again. How might I print out 4 question marks in a row? Not nearly as graphically as that here, but just with my terminal window and text editor. Well, here, let me go ahead and open those two, and in a file called, say, mario.py, let me go ahead and print out, quite simply, 4 questions. I'll go ahead and print out, quote unquote, question mark, question mark, question mark, question mark. Saving that file, again, in mario0.py, running in my terminal window, Python of mario0.py, and voila, do I get a approximation of what Nintendo did in yesteryear. Now, of course, doing something again and again is clearly an opportunity for, say, a loop. And not just printing it all at once, but just doing something again and again. And while this will complicate the code initially, it sets us up for a more interesting solution thereafter. In a file then called mario1.py, let me go ahead and implement that same sequence of question marks, but this time using that familiar loop. Not a while loop or an infinite loop, but perhaps just a for loop like this. For I in the range of 0 up to but not through 4, go ahead and print out just one question mark. Saving that file brings me now to my terminal window in Python of mario1.py, enter. Unfortunately, I've created not quite the right level, but that's okay because remember that with print you get one new line for free every time you call it unless you override that default behavior. So let's say no Python, instead end your line with nothing, and only once I'm completely done do I want you to print one of those free new lines for me. I'll go ahead and save my file again, and in my terminal window rerun Python of mario1.py, and now we have the same exact result. But later in the game, do we see different aspects of Mario's world? Not unlike this thing here, underground. Pictured here are a number of blocks in the underworld, and it looks to me like that bigger block there is a composition of, say, 4. So let's go ahead now and print out a block of bricks, these all represented by hashes, so that I have 4 horizontally, 4 vertically as well, and everything else filled in too. We've not yet printed out anything on multiple axes, if you will, both rows and columns of sorts. So how to do this? Well, in my terminal window, I'm going to create a file called mario2.py. And in this file, I'm going to decompose this problem conceptually, so to speak, into 2 different problems. Built into that underworld are some number of rows of bricks within which are these columns. And I bet I could bite those off each one at a time. So let me go ahead and do this. For I in range of 4, go ahead and print what? Well, for every row of bricks, do I want to print some number of columns too? Because it's a square, the same number of columns as rows, and so I know how to print that many things too. I can simply use another loop, perhaps with a different variable with which to count, like for j, as is conventional, in range also of 4. And then inside of this inner nested loop, so to speak, might I go ahead and print out just one hash, ending each of my lines with as before, nothing. In fact, I only want to move my cursor to the next line after I've printed each of those columns, and so only underneath that innermost loop do I want that call to print. Let me go ahead and save this file now and run Python of mario2.py, and if I've gotten this logic right, I can go ahead and print out those rows and columns too. And indeed, that's what I get. It's not quite a perfect square because those hashes are a little taller than they are wider, but via a for loop, one nested inside of another, can I handle 2 problems at once. The act of iterating from row to row to row, and within each row, iterating left to right via column. And in fact, to make that ever more clear, why don't I even call my variables more aptly? For each row in the range of 4 and each column in the range of 4, go ahead and print each of those hashes. Frankly, it doesn't even matter what I call these variables because I'm never actually using them per se. I'm simply telling Python to count up from 0 to 4 using those particular names. Those then are some programming languages, Python especially among them. And just as we saw in pseudocode, the ability to express functions and conditions with Boolean expressions and loops and then things like variables and more, so can we express those exact same ideas in Python, in C, C++, and Java. And with each of those languages, do you get different features? With each of those languages, do you get different techniques? But ultimately, those languages are all just tools for one's toolkit with which to solve any number of problems with data.